The 4 astronauts aboard Artemis II have flown further into deep space than any human beings in history, looping over 4,000 miles past the far side of the Moon. But covering that distance comes with an immense physical cost. To get back home, they have built up a massive amount of kinetic energy. The Orion capsule is hurtling toward Earth at roughly 25,000 miles per hour, or Mach 35. To survive re-entry at that speed, the approach angle has to be flawless. Looking at this diagram showing Earth's curve, an entry path that is too steep creates too much atmospheric friction. The capsule would face punishing pressure and heat and burn up entirely. On the other hand, if the entry angle is too shallow, the spacecraft will skip off the atmospheric boundary layer like a pebble on a pond, deflecting back out into the black void, with no way to turn around. Adding to the tension in mission control, engineers are closely watching the capsule's heat shield. During the uncrewed Artemis I test flight, the shield experienced unexpected charring and material loss, elevating the stakes for this crewed flight. Bringing this crew home safely boils down to a massive physics problem. NASA has to shed 25,000 miles per hour of speed across 3 distinct, highly perilous braking phases. The first phase kicks off at 7:33 p.m. Eastern. Orion's crew module severs its connection to the service module and hits the edge of the atmosphere at 400,000 feet. To avoid the full thermal load, NASA uses a skip maneuver. Orion dips into the upper atmosphere, rises to cool, then takes its final plunge. During these dips, Mach 35 kinetic energy converts to heat, rapidly reaching 5,000 degrees Fahrenheit on the capsule. Inside the cabin, the physiological toll is severe. The astronauts will be pinned into their seats, enduring up to 3.9 Gs of decelerating force. They also endure this entirely alone. The buildup of superheated plasma around the hull blocks all radio signals, severing contact with mission control for 6 agonizing minutes. Emerging from that fiery gauntlet means Orion has successfully bled off the vast majority of its kinetic energy. The survival strategy now transitions from heat dissipation to aerodynamic drag. Down at 22,000 feet, the air finally becomes thick enough for physical parachutes to grab hold. This timeline tracks altitude against descent speed. At 22,000 feet, 2 drogue parachutes deploy to stabilize the capsule and pull speed to 130 miles per hour. At 6,000 feet, 3 main parachutes unfurl. Speed drops sharply, bringing the descent rate to 20 miles per hour. At exactly 8:07 p.m. Eastern Time, the Orion spacecraft impacts the Pacific Ocean just off the coast of San Diego. The descent speed has been neutralized, but the crew remains in severe peril, locked in a heavy metal cone at the total mercy of open ocean swells. NASA and the Navy now operate under strict parameters. They have a tight 2-hour window to extract the 4 astronauts before seasickness and the physical strain of gravity take a serious toll. The primary recovery vessel responsible for this operation is the USS John P. Murtha, a heavily equipped amphibious transport dock ship. Navy divers immediately deploy in rigid inflatable boats. They approach the floating Orion, stabilize the hull, and attach a floating hauler and an inflatable raft known as the front porch. From there, MH-60S Seahawk helicopters hover above, hoisting the astronauts out of the raft one by one and flying them directly to the ship's medical deck. It is only when the final astronaut steps onto the deck and the capsule is towed into the ship's flooded hull that the spacecraft's velocity is officially brought to 0. Safely extracting those 4 astronauts definitively validates Orion's complex life support and thermal protection systems under extreme, real-world conditions. Artemis II is strictly a flyby mission, but executing this exact re-entry and landing profile is the strict prerequisite for everything that follows. Completing this deceleration sequence provides the immediate green light for Artemis III and IV, missions explicitly designed to put boots back on the lunar surface. Catching a crew falling to Earth at Mach 35 proves that we have the infrastructure to support a permanent lunar base. Mastering the physics of coming home from the Moon is the necessary first step in preparing for humanity's next massive leap, surviving the return from Mars.